welcome everybody to the October MagX. And I just get off as quickly as possible. Stephen McGill will be giving the talk, and our discussant is Dmitry Smirnov. So take it, Dmitry.
Give me another 30 seconds to come back to the office.
Okay, so while we're waiting the 30 seconds, I'll remind people, please mute if you're not speaking. And Steve said if you have a burning question, it's okay to interrupt him. Okay, Dimitri's not moving now. This is good. Okay, but now his earphones aren't connected. Just like me.
We can hear you. Yeah.
Okay. Thank you, Laura. Thank you, everyone, for waiting. It's my pleasure to introduce today's speaker, Dr. Stephen McGill. Steve got his PhD from University of Pennsylvania in 2004. There, under the supervision of Professor J.K. Cower, Steve performed first ever pump-probed optical care studies on so-called callosally magnet-resistive manganites. For those who is not familiar with these effects, I just like to mention that this series of works combine two extremely challenging experimental methods. So it's about detecting very subtle changes of light polarization induced by magnetic field in a system at a very fast time scale, which ultimately enables deciphering spins and charge dynamics. For his postdoc tenure, Steve moved to Tallahassee, not yet to MagLab, but to Martech at the physics department. And he worked there on the project focused on single-wall carbon nanotubes under the supervision of Professor Peng Xiong and Stefan von Wollmer. Finally, in 2006, Steve joined the MagLab, bringing his expertise in optical spectroscopy, in particular, of course, in fast and nonlinear spectroscopies, to the realm of our very high magnetic fields. And you probably already know this, that there is one very special magnet in MagLab's arsenal that provides a unique fit for this kind of spectroscopies, a split Florida Felix magnet. Nothing comes for free. Performing measurements there is always a challenge, and I'm sure that Steve is going to explain more about these unique features and unique challenges. So I'd like to remind you that it will be a 20-minute presentation followed by 10 minutes questions and answers and discussion session. Please make sure that your mics are muted for the duration of the talk. Please feel free to post your questions in the chat window. And if you think you have an absolutely burning question that needs to be addressed immediately, of course, it's okay to unmute and ask it. Now, Steve, the podium is yours.
Well, thank you very much, Dmitry, for that introduction. Thank you, Laura, for the invitation to do this talk, and thank you to everyone else who has joined to come hear my talk. I'm going to be talking today about magneto-optics in, of course, that favorite magnet of mine that Dmitry just mentioned, the 25 Tesla split Florida helix. And I just want to point out that this work is not the only work that's being done there. I am just talking about the work that I'm associated with. For example, there is another group that's working on X-ray scattering as an example. So in my work here at the MagLab and with this magnet and users, there's a few common questions that I get very frequently. And what I want to do today in giving you an outline for my talk is to go through about 4 of those very common questions. So number 1, what makes the 25 Tesla split Florida helix magnet special, and what research limitations does it remove? 2, what role does light play in the physics of materials? 3, what physical insights can optical spectroscopies offer? And then finally, 4, what are some examples of research done in the split Florida helix magnet? Well, first of all, and you'll be able to follow along here with the different questions I posed in the outline up here in the upper top if you get confused about what section or question we're talking about. But the first one is, what makes the split Florida helix unique? Well, you can look over here on this picture, and these yellow cones are describing the wide optical ports. This is what makes this magnet completely different from any other magnet in the world, is the free space optical scattering volume that we can access to send light in and receive light out through the sides of the magnet. There's 4 11.4 degree by 45 degree openings around the midplane of the magnet. Here's a cross section through the split helix. Here is where the high field point is, and you can see we can send our light in through the side. No other magnet provides this much combined optical scattering volume and magnetic field. Now, why is it called a split helix magnet? Well, you can see here in the cross section that there's actually 2 helixes, 2 magnets, one on the top and one on the bottom. And it's split in order to open this gap so that we can send light in. If you've ever taken 2 magnets and tried to hold them together and they're attracting each other, you know that that's very difficult to do. So the engineering that went into this is just fantastic. And so we can use a dewar to insert through the bore of the magnet and chill our samples here. Before, the only way that we could get light in through free space methods was to go up through this narrow long bore or to use optical fibers. And so the significant limitations that are imposed by using optical fibers, there aren't optical fibers that allow you to use any kind of optical light that you want to, that is removed because now we can send the beam in through free space, and the alignment of the experiments is also greatly simplified by being able to go in through the side. And I can't leave this without highlighting just the great work by the MS&T, especially Jack Toth, who was the lead designer of this magnet. It is just a phenomenal system, and it has enabled the ability to do the kind of experiments that I work on. So now, question number 2, what role does light play in the physics of materials? Well, when we first learn about atoms, there are some facts that we are commonly told to help convey the basic concepts of atomic structure. And one of those very famous and common ones are that there's a nucleus where the protons and the neutrons are, and then surrounding that are where the electrons reside. So just to bring that into like a real world perspective, imagine now that the nucleus is the size of this blueberry. And if we take that blueberry and were to put it in the center of Doak Campbell Stadium right there on the field, then the size of the entire stadium would be approximately the size of the atom. And so this conceptual model is given in order to relate that the nucleus is very small compared to the overall size of the atom. So, you know, when you're in high school, you sort of start out, we all start out with this rather naive atomic model that's shown here. And other than the nucleus, we know that there are these electrons, and then what else is left in there? Is it just space? Well, if it's just space, then the next time you try to grab a cookie before dinner and you get caught, try this explanation on mom or your spouse. But mom, this cookie is 99.99999% empty space. Well, we know that's ridiculous. And in fact, if we go on to look at a less naive model of the atom, we know from classical field theory, for example, that it's the electromagnetic field that fills the volume between the electrons and the nucleus. And if we go on further into quantum field theory, electrons themselves are described as excitations, delocalized in the field that fills the volume of matter. And as you can see here in this Feynman diagram that is describing the scattering of electrons, it's photons, represented by gamma, that carry the information that passes between electrons and between the electrons and the nucleus. So here's the answer to the question: what role does light play in the physics of materials? Since the volume of matter is mostly fields of electrons and photons, it's reasonable to expect that much of the physics of condensed matter is electromagnetic. What is it that makes that cookie a cookie? Well, it has a lot to do with the interactions between the electrons, the bonds that exist there. Your body understands this because in our stomachs, we have a chemical furnace, and we know that we can gain energy by breaking the bonds between the molecules in that cookie. So there you have an example of what role that plays. Now, moving on to question 3. What physical insights can optical spectroscopies offer us? Well, over here on the left, I have a diagram that gives a continuum of the energy or the wavelength range of different parts of the electromagnetic spectrum. Now, I tend to work over here in this visible to near infrared side, but a lot of work in time-resolved optics, which as Dimitri mentioned is one of the areas that I specialize in, can cover an even wider range out to the terahertz regime, even the far infrared section of the spectrum. And this itself is just a subset of the entire electromagnetic spectrum. It can extend out further beyond the UV to X-rays and gamma rays. And so the idea here is that in this picture, there are different electromagnetic phenomena, different broad classes of those phenomena that can be accessed or studied depending on how you tune the light that you're using to study the materials. So since electromagnetism plays a significant role in materials physics, there's much to learn by studying the light that interacts with the material. And optical spectroscopy is not only about the observation of these electronic phenomena, but also about using photons to control or tune the material properties. And so again, here, this is just a few examples of those types of phenomena. Now, I want to talk about different types of spectroscopies, and I'm going to use this traffic light here as an example. So in time-integrated optical spectroscopies, like emission and absorption, those kind of spectra will chart important photon energies that electrons use to communicate material-specific information. And you can see here on a typical like detector chart, those different frequencies. There's the green of the green light, the yellow of the yellow light, and the red. And there's quantitative information in everything that is collected here. The energy, which is given by its position here in wavelength, the shape, intensity, and the polarization even, which is not shown here, of the spectral line, all contain quantitative physical information. However, there's still more that can be gathered. In time-resolved optical spectroscopies, the data can provide dynamical information about transient states, patterns, and even the durations of different electronic phenomena. So for example, a very famous historical example is the question of whether all 4 hooves of a racehorse simultaneously left the ground during the racehorse's stride. And the answer, of course, was yes, that does indeed happen. And if we bring this now back to our traffic light example, and we use time as one of the variables that we're recording, you can see that we get information about the duration, the pattern, the order in which these lights come on, and the fact that one is on and none of the others on. They're on individually at different times. So here's the green light coming on, the yellow light, and the red light. So again, we're getting information about these transient states. So time also allows us to get an additional set of dynamical information. And so now let's move on to ultra-fast time-resolved optical spectroscopy, the kind like is often done at the MagLab. So a camera was used in order to see whether the horse's hooves came off the ground all at the same time. But you're going to need a much faster light source and camera to record transient electronic dynamics. So for example, if we use the pulsed laser source and we chart the electric field amplitude of the light coming out versus time, commonly the time between pulses can be anywhere from milliseconds down to microseconds, maybe even nanoseconds. But on the scale of the time between pulses, those pulses themselves look like Dirac delta functions because they're so short in time. So if we were to zoom in on one of these pulses and expand it out, and look at the electric field versus time, here you can see on the x-axis that the time is being recorded in femtoseconds. That's 10 to the minus 15 seconds. And just to put that in perspective, if you viewed time passing such that 1 femtosecond was like 1 second, then 1 second would be like 32 million years. So there's a lot of femtoseconds in 1 second. So this is very fast. And you can see the pulse packet here of the electric field for that light pulse. Here's sort of a 3D rendering of a circularly polarized pulse where you can see the rotating electric field. And so ultra-fast pulses like these have a large instantaneous power due to their very, very short durations in time. And that enables the ability to do research into nonlinear processes and non-equilibrium states. So by non-equilibrium, I mean, take a pulse of light, send it into the sample, it's going to drive the material away from equilibrium, and we can watch how the energy rings throughout the different subdegrees of freedom in the material and recovers back to its equilibrium state. That's one example of the type of work that you can do. And here's an illustration of exactly that kind of spectroscopy. This is called pump probe spectroscopy. Here is a representation of the sample. We can have our detectors, which form our ultra-fast camera. We can collect the light in transmission or reflection, for example. The pump pulse comes in. Let's say we use an optical excitation pulse to drive or to excite, the sample. And then the ultra-fast dynamics are going to be recorded using a time-delayed, weaker pulse that we call the probe. And you can see here how it's time-delayed, 1, 2, 3, 4, 5, and 6, corresponding to these snapshots in time. And as we collect those in the detector, we can build up different dynamics of the electrons in the system, different electronic phases or states. All right, let me give you just a concrete example of that. Again, we're talking about what physical insights can optical spectroscopies offer. One example here is, and this data was not taken at the MagLab, but imagine you have a charge density wave system where the charge is varying here according to these particular wavelengths. And we send in a pulse to excite the system. Oftentimes, optical pulses are used to transiently melt electronic phases. So it comes in and it destroys here at 0 time that charge density wave. And then we watch how that order parameter for the system recovers. So for example, there's 2 particular energies. Here's our time axis. Here's the frequency of the light that's being probed. And so what happens is we can see that there is an amplitude mode of the charge density wave just above 2 terahertz. There's also a phonon mode that exists just below 2 terahertz. And initially, the amplitude mode of that charge density wave, which is here and seems to recover out around 6 picoseconds, initially is destroyed. It's melted right at 0 time when that excitation pulse comes in. And then we can watch the intermediate states as that recovers. Here, for example, there's some odd line shapes happening where it's sort of asymmetrical and diagonal. And so just as an example, what happens is we can chart sort of the free energy landscape versus the order parameter, let's say, on the axis represented by the charge density wave. Maybe there's a sample where you have a charge density wave that's competing with superconducting order. Well, if we imagine time, the ultra-fast time along this axis and energy along this vertical axis, then the optical excitation pulse can come in. It can change that energy landscape. The position of where we are in that is represented by this ball. That can change. We're now in a different phase, and we can fall in to different local energy maxima that otherwise would not be accessible. And so finally, what I want to come now to is question 4 and provide you with a few examples of research that has been done in the 25 Tesla split helix magnet. So for example, this is a group Greg Scholes' group that came, and the title of that work was How High Magnetic Fields Change Non-Magnetic Molecules, How They Absorb Light, and the Properties of Their Excited State. So this was an ultra-fast pump probe measurement. It was a broadband transient absorption measurement. We're looking at the transient transmission of the probe through here over a range of wavelengths. And you can see here is the time-resolved dynamics of these porphyrin molecules. And there are delocalized electron pi states. And when you turn on a magnetic field along the axis of these molecules, the field changes the intersystem crossing dynamics. So here it is at 0 Tesla, black being 325 femtoseconds after the excitation pulse. And then here we have the same measurement at 25 Tesla, the black one being very different relative to the data at very, very long times, which is a sign of the relaxation back to the steady state. And it has changed that behavior there. And so these systems are often considered as platforms for spintronics or quantum computing. And so this gives us an understanding of the charge dynamics that are happening on short time scales in these materials. Now, here's a completely different example that is done by Jan Musfeldt's group. So as we were talking about earlier, sometimes light's used to control or to tune the properties of the system. Well, here's an example of a ferroelectric ferromagnetic system. It's a superlattice of lutetium iron oxide. And it's a superlattice with different valencies of the iron oxide and different numbers of layers of those valencies in between and stacked. And it turns out that these different ones have different Curie temperatures. So the goal here is, can we engineer a system that is both ferroelectric and ferromagnetic at room temperature? And so because there's such a large change in the Curie temperature, we'd like to know what's going on in the magnetic system. Well, with light, we can do that. So by doing a measurement called magnetic circular dichroism, we can look at the hysteresis loops in the material. And because we can do this for different wavelengths of light, we can get an idea of how the interface magnetism is changing in an energy selective way. So for example, one of the things that was discovered here is that for different combinations of layers in the superlattice, the spin-up charge channel for the Fe2 to Fe3 plus transition, which was at about 2.2 electron volts, got larger. And so therefore, this explained what was going on in terms of the enhanced magnetization in this system, because the MCD signal was proportional to the magnetic moment in the material. And we could chart the closing of the hysteresis loop in order to see different thermodynamic energies of the system and how they changed. And I know I'm getting close to my time here, so I'm just going to wrap up with maybe one or two more examples. Here's another one also done by Scholes' group. This one is called High Magnetic Field Detunes Vibronic Resonances in Photosynthetic Light Harvesting. Here, for example, is a protein from a living organism. It's an algae protein, and it has different chromophores throughout it. These chromophores act as an antenna to capture light energy and then channel it into the chemical work centers of the cell. Here's what the absorption spectrum of that looks like. We recorded how that changed after we excited the system in a specific part of its spectrum here. And then by analyzing the changes in the absorbance, we were able to identify the fact that the chromophores use actual electronic resonances in order to transfer the energy from the antenna down into the centers where ATP is created. And it took a high magnetic field in order to detune that and demonstrate that it was indeed there was an electronic component and not only just a vibrational component to that. Okay, and I see that my 20 minutes is up. So I have given you a few examples And I just want to end with the acknowledgement of several people. Of course, there's all of the users who came and did the work that I have described. And I really want to also highlight my thanks to Dmitry Semenov. He's such a key person in all of this work. Without his work designing the cryogenic probes that the users have used to make these experiments possible, and taking care of the cryostats and making optical tools, none of this would have been possible. And so thank you very much for that. And that concludes my talk.
Thank you very much, Steve.
Okay, thank you.
So I don't see any questions in the chat window. So now please free to ask questions directly.
I actually do have a question.
Yeah, sure.
In the photosynthetic light harvesting,
Right.
I didn't see the field dependence on that. Could you explain how
Right.
the field separates the bonds or,
Yeah,
or
so-
the resonances?
Well, so there's an intermediate state that it has that's a singlet state, and the field moves the energy of that intermediate singlet state. And so there's a singlet state. Actually, there's two states, two excitonic states in the once it's excited, and those two overlap with each other. Let's see. What you can see here, this is the only example of this that I can show you here in this presentation. But essentially, if you take that time resolved data, there are some oscillations. There's some periodic oscillations in there. And those periodic oscillations are, well, the period of them is proportional to the energy separation of the overlapping excited states. And so we see those here, and these are the different energies and wave numbers of what those are. There's one here that's a reference that has a portion of it removed, but here are the two identical chromophores at 0 field and 25 Tesla. And you can see that there's a very strong, the amplitude of this signal is a sign of how strong the resonance is between those two excited states. By turning on the magnetic field, because it has a spin singlet state, it is displaced in energy at 25 Tesla. And because those now move apart in energy, that has been detuned. So that's the essence of the detuning there.
Okay. Interesting. Thank you. Very interesting.
Steve or Laura, somehow I don't have co-host privileges, so could you please unmute participants?
I think participants have to unmute themselves.
Okay.
I have
Okay,
a question.
I see Ryan has his hand up. Yeah.
Yeah, so I'm pretty simple-minded. I have a pretty simple question, I think, but
Okay.
it seems to me like in the pump probe experiments, like the type of material that you're interested in, you gave an example of charge density wave versus superconductor. So it would be sorts of materials that have two closely spaced potential ground states. And then you can pump it and look at how it relaxes between the two. So my question really is just this, that gives you an opportunity to look at complexity, but how do you make a choice about what is a good material to look at? How do you choose which experiments to do?
Yeah. Great question. It is not always easy to know. Typically, the time resolved measurements, since they take more effort to do, typically follow after a lot of steady state spectroscopy is done. Okay, so you may find, for example, that particular optical resonances have already been identified, and we know that they change because people have done the absorption or the emission measurements, tuned various thermodynamic knobs like temperature, magnetic field, and said, I noticed that absorption is changing when I, go through this phase transition, or, something else is happening in the sample. So that gives you kind of a clue that, maybe there is something there that is connected or correlated in some way with the phenomena that you want to study. That's one way, okay? But yes, you're right. In some cases, you don't know until you start looking into it, and it's typically not the first experiment that you would try.
Okay.
So you would rely on the previous literature to give you a clue of what might be an interesting experiment to look at and to help you choose the material. Right?
Okay.
You can't just pick anything, off that has some sort of if you don't know sort of the energy landscape ahead of time.
I see. Okay.
I see.
Okay. Yeah. Thank you.
You're welcome.
I have a question, if I may.
Absolutely.
Yeah, Steve, you show the use and examples related to the transit processes, polarization control. Another thing where this spectroscopy and magnets is very useful is nonlinear spectroscopy.
Yeah.
And in the field, what I'm working in, like for example, Moiré heterostructures.
Yeah.
Second harmonic generation is proven to be a very efficient tool.
Yeah.
For a variety of aspects. Can you do this?
So I have the nonlinear pulses or the ultrafast pulses. I have done actually some second harmonic generation measurements. I did some looking at antiferromagnetic symmetries in a transition metal oxide a few years ago. So I've done it. It's not a measurement that I've done frequently, but yes, that's something that I have done in the past.
Okay.
So yeah, for example, there's second harmonic generation. A number of these experiments are, well, so for example, when you apply light to a system, you're inducing a polarization. And some of the effects, like four-wave mixing, which is something that Dennis Karaszkai's group has done, is related to like the third order nonlinear polarizability tensor. So, there's this susceptibility tensor, right, that's connects the electric field applied to the polarization that's generated. So, there's a number of different forms of nonlinear spectroscopies. But yes, having these really high peak intensity instantaneous power pulses really helps that to make those kinds of measurements possible, because the signals are weak.
Good. I think we have time for maybe one more question. Please use this chance. Somebody?
I have another dumb question.
Go ahead.
Okay. I think that I noticed that a lot of the materials you measured are more on the insulating side of things.
Yes.
And I'm do this as purely for selfish reasons. I make a lot of things that are more on the metallic side of things. How hard is it to do measurements on more metallic samples?
You can do measurements on metals. It just is that I think historically, based on the things that I have done in my graduate work, for example, and then here, a lot of the systems are not necessarily metals, but they're dirty semiconductors or poor metals.
Mm-hmm.
They have some sort of insulating character to them. But yes, there is a large literature of ultrafast work that's done on metals. I haven't been involved with a lot of it, but one of the ones that I can think of, for example, is that there was work on metallic ferromagnets and half metallic ferromagnets. And so that was some work that was done a few years ago in order to see how quickly optical pulses could switch, say, the magnetism in those samples, their magnetic moments. So yes, that can be done.
Mm-hmm.
And one of the things is you're kind of limited on, especially if you're working on a bulk sample, because depending on the energy range, and if you work in the optical range, which I tend to do, transmission, unless you have a very, very thin film of the material, is hard, because you're going to, unless you're, below the range at which the carriers respond, it's going to be reflected. But you can do the measurements in reflection, as I showed. For example, the Kerr effect measurements that I did, again, looking at the magnetic dynamics in manganites, were done in reflection. Kerr effect is by definition in reflection. And so there are magneto-optical effects, for example, that you can look at. And there are other techniques that can be used on metals.
Okay, cool. Thank you.
Yeah. Thank you, Steve, and thank you all for
Terrific.
being with us. Laura, any comments, words to end the talk?
No, great talk, Steve. Great monitoring, Dimitri. And thanks for coming, everybody. And keep an eye out for a month for the next MagX talk. So thank you, everybody.